Look around at the objects and organizations that fill our lives, and you'll notice a pattern. Things generally don't work very well. The train is delayed, the software crashes, the bureaucracy takes 6 months to process a simple form. When a project collapses or a service breaks down, we naturally point fingers. We blame bad management, we blame a lack of funding, or lazy employees, or poor planning. We assume that if we just had the right people in charge, everything would run smoothly. These excuses ignore a more difficult reality. Breakdowns are a natural, unavoidable feature of systems themselves. In the 1970s, a pediatrician and systems theorist named John Gall articulated what he called the fundamental theorem of Systemantics. It states simply, new systems mean new problems. To see this in action, look at a municipal garbage collection system. We create the system to solve the initial problem of waste in the streets. We call the effort required to align the world with human desires energy. But once the collection system exists, that energy doesn't disappear. You now have to negotiate union contracts, repair broken-down trucks, secure budget approvals, and manage voter apathy. The trash might get picked up, but the sum total of difficulty facing the community remains identical. Systems redistribute that friction into larger, more complex forms that demand our constant effort. This leads to the operational fallacy, the observation that a system does not actually do what it claims to be doing. If you want a fresh apple, you could walk into an orchard and pick one right off the branch. That is a minimal system approach. But most of us rely on a massive supermarket supply chain to deliver that same experience. Trace this supply chain flowchart to see why the large-scale system cannot deliver a tree-ripened apple. To survive transport logistics, the fruit is picked green, sprayed with chemicals, sealed in controlled atmosphere storage, and artificially ripened using exotic gases. We still call the final object a fresh apple because we are victims of the naming fallacy. We accept the chemically stabilized sphere in the produce aisle because it wears a familiar label, despite bearing little resemblance to the original fruit. The system's true output is designed to satisfy the system's own logistical needs. The product is defined strictly by the operations required to manufacture it. This exact rule applies to people working inside these structures, an effect known as functionaries' falsity. People rarely perform the function assigned to their titles. Think of a university botany professor. Their stated job is to study plant life, but in reality, they fill out grant applications, attend endless committee meetings, and draft objectives reports, all to satisfy administrators. In chemistry, Le Chatelier's principle states that natural processes tend to set up conditions opposing their own operation. Human organizations behave the exact same way. The administrative structure built to support the botanist eventually consumes all their time, preventing any actual botany from taking place. The moment a system is born, it develops internal goals, operating regardless of its designer's intent. It prioritizes its own survival and expansion. You can see this in massive infrastructure projects, like the Aswan High Dam in Egypt. It was built to tame the Nile River, generate electricity, and improve the lives of local farmers. Look at this cyclical feedback loop to see the exact point of conflict. The dam blocked the natural, fertilizing silt from flowing downriver. To keep the crops growing, the country had to build massive artificial fertilizer plants. Those new plants require immense amounts of electricity to operate. So the dam now has to run at near capacity just to power the factories required to fix the agricultural damage it caused. Once a system reaches a certain size, it no longer serves its creator. It serves its own insatiable need to persist. Because reality is complex, large structures operate almost entirely in a continuous state of failure. According to the generalized uncertainty principle, they act in ways that are totally unpredictable. Even our most rigorous safety designs fall victim to this rule. Take the Enrico Fermi fast breeder reactor in Michigan. Engineers installed a specific safety device there to prevent a meltdown. But during normal operations, that exact fail-safe component broke off, blocked the flow of liquid sodium coolant, and directly initiated the meltdown sequence. When a fail-safe system fails, it fails by failing to fail safe. When confronted with these breakdowns, our instinct is to push harder on the machinery, demanding it work better. But forcing a malfunctioning system usually just triggers further collapse. we have to accept that error is our existential default. The most vital concept in our vocabulary is the word oops. Every glitch is a piece of data showing us exactly how a structure breaks down. Surviving uncontrollable systems requires the skill of a navigator. We thrive by constant course correction, reacting to waves of failure as they arrive.